Okay, in this video I'm going to demonstrate how to carry out a latent growth curve model when you have two domains in which you're studying growth on. The example comes from Barbara Burns' book, Structural Equation Modeling with AMOS, and the data set was downloaded from this website right here, and the examples are provided from chapter 11. So the data set, by the way, looks like this. This is the raw data that I downloaded. You'll notice that we've got a number of different variables. The ones we're going to focus on are perceived math ability and perceived science ability, measured at time 1, at time 2, and at time 3. And we also have a variable student sex, which is coded 0 for female and 1 for male. So at any rate, that's what the data set looks like. So to draw our model, what we'll do is we'll go up to plugins and growth curve model. And when I click on this, the default number of time points is 3. And you should not be doing growth curve modeling with fewer than 3 time points. So this is the obvious default. You can set it higher if you have more time points that you're working with. So we'll click on OK, and then it will draw out this model right here. So the next thing to kind of take note of when you're looking at this particular model is you'll notice that the rectangles are basically going to be utilized for the repeated measurements on our variable, either perceived math ability or science ability. The intercept and the slope, these are factors, and these factors represent components of the individual student's growth curve. So you can imagine that each student will have a particular intercept and a particular slope representing their growth curves. You'll also notice that we have error variances associated with each measurement occasion as well. So you can see the model looks pretty much like a conventional confirmatory factor analysis where we have two factors and that they are correlated. So what we'll do, first thing is let's pull the data into this program. So I'm going to go to select data files and file name, and I'm going to select the file and click on open. And so you'll notice that we have 500 cases, that's 500 students with the repeated measurements. So now when I click on OK, the data has now been imported into the AMOS program. And so let's now a few things to kind of look at. First of all, what I can do is let's just go ahead and move our repeated measurements for perceived math ability over. So I'm going to click on this little button right here and scroll down, and we have math ability. I can move it over for time 1, math ability at time 2, and scroll down, and then math ability at time 3. So you can see that the variables kind of extend beyond the box, and these were the labels that were actually in the raw data file. So if I want to clean things up, I can click on Object Properties, and when I go to the text, you'll see this is the original variable name that was in our data file, and then the labels that you see are these labels right here. So if I want to change the labels, then this is where I want to work. Theoretically, I could change it. I could say PMA1, and so forth, or I can just kind of reorient things a bit. And I'm just gonna hit enter here and kind of clean things up in this kind of way. All right, so there's perceived math ability. Now, other things to kind of go and take into account, because what I want to do is I want to copy this particular figure and then just kind of feed in the science ability variables to kind of make things a little easier on me. So, I'm going to go and do whatever editing at this step first before I copy this figure over. So the next thing is I'm going to, you'll notice that the VARs right here, basically what happens is that any parameter that is has the same name across a set of variables or whatever, basically the parameter is treated as fixed across, meaning that we're estimating the same. In this case, the variance is assumed to be equal across these 3 measurement occasions in terms of the error variance. So if I want to allow the error variances to be freely estimated, which is really probably more tenable, I'm going to right click here, click on Object Properties, and then click on Parameters. And here what I'll do is I'm going to remove this for each of these variables so that now the error variances can be uniquely estimated. Next, what I will do is you'll see that the intercept, the paths from the intercept factor to each of our repeated measures, those are all fixed at 1, and we want to leave that where it is. For the slope, the fixed effects, basically if I want to model a linear growth trajectory, then a lot of times what I'll do is I'll go ahead and reset these paths at 0, 1, and 2. So basically representing an increment of 1 across paths. So the path from slope to perceived ability technically does not need to be there, but we're going to leave that in there at 0, and I'm going to right click on this arrow and I'm going to reset this at 1 and 2 right here. Okay. Now, the other parts, I'm going to also free the variance and means for this factor and this factor. And also, I'm going to go ahead and remove the covariance here. So, because what's going to happen is when I generate these new variables, I want the parameters to be freely estimated. So. Okay, so now I have basically a growth curve model for perceived math ability, and this is assuming a linear growth trajectory. Next, what I'll do is you'll see that I don't have a whole lot of workspace, and so what I'm going to do is go to View, Interface Properties, and click on Paper Size, and I'll just go down to Landscape Legal and Apply, and you'll see that now I've got a lot more white space to work from. And if I use my little tracker on my mouse, kind of go up and down, you'll see that the figure still kind of extends beyond our workspace. And so what I'll do is I'm just going to select all objects and click on my little moving truck right here and move everything up a little bit. You'll see it gets a little wobbly there, so you got to be a little bit careful about that. So I've kind of moved that up and I'll deselect. If it's the case that I want to kind of resize some of these things, which I might, I can click on this little button right here, and you can see I can kind of resize there and the same here, so that I can kind of have a little bit more space to work from there. So there you go. All right, so I'm going to click off that little button, and now I just want to copy this stuff over. And so so what I will do at this point is I'm going to hit my little copy button right here, select all objects, and then I'm going to drag. So when you select all objects, everything is selected, and I'm just going to I'm just going to drag this over here. And there you go. So now we have this figure as well. If I want to, so you can see that it looks like we're kind of extending off the page a little bit. So I'm going to deselect and reselect, and now I'm just going to use my little moving truck to kind of move everything over a bit right here. So everything's kind of centered a little bit better on the paper, and then click deselect objects. So now now we have our figure. And so now what I can do is I can move my new variables over here for perceived science ability. So I'm going to click in this little button right here and go up and go to perceived science ability. I'm going to move it over to this box right here, and then do the same for perceived science ability right here and perceived science ability right here. And then I can just do some of the same things that I was doing earlier with the math ability, which is go to text box, and if I want to kind of clean things up a little bit, I can do this like this. So there's the drawing, or if I want to kind of straighten this up, I can change the font size as well. I can just basically say, well, I want to make font size 18 or or 16. I can do that. I can do this for each one of these. I just click on this and then move, change it to 16 here, and the same for here. I can just change my little font size. So there you go. So now we've got essentially two growth curves. Now if I want to allow the intercepts and slopes to covary in terms of both growth trajectories, I can do that. So if I allow the intercepts to covary, then essentially what I'm saying is, or I'm hypothesizing is that the starting uh, levels of perceived ability in math or science, um, that there's a relationship. For instance, if the because that's essentially what the intercept is representing in these models is essentially time one value or time one score or whatever on perceived math ability and science ability. So let's say, for instance, that this covariation right here, or this covariance is positive. That would indicate that those students who tended to exhibit higher levels of math ability at time one also tended to exhibit higher levels of science ability. If the covariation is negative, that would indicate that those who were higher on perceived math ability at time one will also be lower on perceived science ability at time one. The slope parameter, we can also allow that to covary as well. And so if we do that, then what we're assuming is that the changes that might be observed in perceived math ability might also correspond to changes that we observe in terms of perceived science ability. So these are a couple of ways to do this. We might also theoretically have expectations about a relationship between the slope for science ability and the intercept for math ability and so forth. But these actually seem like fairly more logical assumptions about some of these relationships here. Basically kind of within domain correlations between intercepts and slopes, and then across domain correlations in terms of the intercept and slope parameters. You'll notice that we're kind of falling off the page again. And another option is to use a little resize option right here. It kind of makes it a little bit messier. Sometimes we might have to kind of go back and reorient, do our text and kind of resize a little bit, as you can see right here. It's a little bit of a hassle, but it's not the worst thing. At least you can kind of clean things up if you want. So that's what I'm kind of illustrating right here. There's 16 right there. Okay, so you can see that, and then you can also see that science ability is kind of falling off the page, or falling out of our boxes as well. So you can do that. I'm not going to bother with anything else on that, just to kind of show you some options here. So at any rate, so now what I'll do is I will click on my little Calculate Estimates button, and it's going to say, oh yeah, and this is another thing. Now that we've copied, I have to make sure that these are unique names for intercept, slope for each of our growth curves. So I'm going to just click on Object Properties. I'm just going to rename this and resize it too while I'm at it. I'm going to resize this and then name it Intercept for PMA for Math Ability, and I'll just resize this as well. And we'll do Slope for that as well. So I'll just kind of go down here and Slope for Perceived Math Ability. And then we'll do the same for the other two variables. Not that I really have to at this point because they're unique names, but we'll just do it in the interest of consistency. So intercept for perceived science ability, and do the same for the slope. Okay, so there you go. So now, because if you don't have unique names associated with your variables, then it's not going to run. Also, you'll notice that we also have the same problem with respect to our error variances. So we already have 1, 2, and 3 right here. So I'm actually just going to rename this E4, E5, and E6, just to make life a little bit easier on us. And there you go. So all our variables now have a unique name associated with them. So now when I click on estimates, you'll see it says proceed with the analysis. And you'll notice that by default, what it's essentially doing is saying, hey, you're you have two of your factors that you have a couple of factors that are uncorrelated. That being the intercept for perceived math ability and the slope for science ability, slope for math ability, and intercept for science ability. And so, we could actually specify those correlations. The analysis will run with this. Even so, we can click on proceed with analysis, and then what we have to do is we have to give our project a name. So I'll just stick with this name right here, and actually I'm just going to override a previous run through in this demonstration. So now, running the analysis, we can see we've got under model fit, we've got our chi-square goodness of fit test. You can see it was statistically significant, which we don't, basically when it comes to interpreting the fit statistics with a latent growth curve model, we interpret them pretty much the same way that we do in standard structural equation modeling. So the chi-square goodness of fit test is one way of looking at fit. In the past, it was emphasized a little bit more as a statistical test of fit, and if it was significant, that would indicate that your model was not fitting the data particularly well. Given that the recognition that the chi-square test is impacted by sample size, and that even with modest misspecification, it can be statistically significant. This tends to be a little bit more de-emphasized. So we can also look at the, excuse me, the CFI and the TLI, and really what we're looking for are values that are optimally above 0.95, but in the 0.9s tend to be still reasonably acceptable values. So these are really suggesting good model fit to the data. The RMSEA value is 0.077. Optimally, the values would be 0.05 or 0.06 or below, which would be more suggestive of a close model fit. But values up to about 0.08 are considered still reasonable or acceptable. And then values above 0.10 might be considered indicative of really mediocre or poor fitting models. When we look under the estimates, you'll notice that we have our previous specification for all the paths, and really the regression weights and in this file right here, or this table, don't really tell us a whole lot. When we look at the we have our means for the intercept, which is essentially basically an average across individuals for their time ones in terms of perceived math ability, and intercepts for time one for science ability. We also have the slopes, and so this is basically essentially an average slope for math ability across the individuals, and an average slope for science ability across individuals. So you can see that on average, the students tended to exhibit decreasing perceptions of math ability over time, whereas with respect to science ability, we actually see increasing levels of perceived science ability over time. When we look at the correlations between our factors, you can see that the intercept for math and slope for math, they were there's a negative covariance between them, and it's statistically significant. And really what that tells us is that those students who started off at higher levels of math also tended to exhibit less change in terms of the slope for perceived math ability over time. Whereas when we look at the intercept for perceived science ability and slope for science ability, we see essentially no relationship. So there's no relationship between where students started out in terms of science ability and their rate of change over time. When we look at the intercepts between the math and science, or the relationship between the math and science intercepts from the students' growth trajectories, we see that there is a positive relationship. So all things being equal, students who tended to exhibit higher levels of perceived math ability also tended to perceive higher science ability at time one. And then when we look at the relationship between the slope parameter for the students in math and science, we see a positive relationship between them and a significant relationship. So, so at any rate, at this point, let's transition just a bit and just kind of following a little bit more closely with the presentation in Barbara Burns' book. In her final model, she actually incorporates the math and slope and intercept correlation, the science intercept and math intercept correlation, and then the math and science relationship here, but not a relationship here. So let's remove this path, and we can rerun the analysis. Also, yeah, I mean, I could also theoretically, if I wanted to, under output, and what she did in her book was she actually used modification indices to kind of decide, make some decisions about paths to prune and so forth. So and theoretically maybe to add. She's kind of suggesting that. So at any rate, I can ask for that. I could also theoretically ask for standardized estimates as well. And just this is more just a FYI more than anything else for you. So I'm going to proceed with the analysis and just kind of show you again model fit. There's a model fit. Really, it doesn't change anything by doing what we with that one respecification. Basically, again, we have the same similar parameter estimates in terms of the means for the intercepts and slope parameters for the students, or the average intercepts and slope parameters for the students, and then the similar covariances that we were kind of noting before. The last thing that I want to show you from her example was she also incorporated students' sex as a predictor of variation in the growth curve parameters. So basically what she incorporated was sex as a predictor of the students' math intercepts, math slopes, science intercepts, and science slopes. So the way that she did this in the AMOS program, well, first of all, here's what we'll do. We need to actually get some room in here to model that. So what I'll do is I'm going to select all objects again, click on my little moving truck, and kind of move everything up a bit, and then click off. And then so the next thing is I'm going to add a gender or a sex variable in here. So I'm going to draw a little rectangle here, and then move over. I'm going to find my variable, there's sex, and move it over here. And in this case, now what I need to do is I have to draw arrows from sex to each of these growth parameters. Now you'll notice what happens when I do this. You'll notice that I can't really do it in this kind of way. And the reason why is because I have to take into account the fact that now I've got a predictor of these variables, and so there has to be error variance associated with with each of these variables. So what I'm going to do is I'm going to erase all of these covariances that you see right here, and now click on each of these and kind of move it around. And so these are going to be disturbance terms, so basically reflecting variance in each of these growth parameters that's not accounted for by sex. So I'm going to double click off my little button there and go to right click, and under object properties I'm going to type in D1 for that variable, D2 for that, D3, and then over here we'll go to D4. And so now I can draw the paths from sex to each of these variables. In this kind of way. So now I can talk about the relationship between student sex and their individual growth parameters. So at this point, what I'll do is I will let's run it. Let's really quickly. I just want to take a quick look at one other thing here. You'll notice that sex is coded 0 for female and 1 for male. So when I go under here and run the analysis, that will be important for understanding the relationship between sex and each student's growth parameters. So now what I'll do is I'll click on Calculate Estimates, and then go to View Text, and you'll notice under Model Fit, the Model Fit is actually worsened, and that's because I didn't actually follow exactly the model that Barbara Byrne had laid out in her textbook. She actually incorporated covariances among some of the disturbance terms. And so essentially what this is we were treating the relationship, sex as a predictor of these variables and ignoring the fact that some of the variation, as we saw in our previous models, that part of the variation in these factors right here should be covariant. So just to be consistent with that, let's add those in. So I'm going to add in a covariance between disturbance here and between these disturbances here, and then the disturbance between these two factors here. So I believe that should pretty well nail the model that is presented in our text. So let's rerun it. So I'll click on Calculate Estimates again, and when I click on my little box here, Model Fit, you can see we're in better shape. So you can see we still have a significant chi-square value. The CFI is 0.973, which is indicating good fit. TLI is same. Our MSEA actually drops a bit, which is indicating a better fitting model than what we had had before. Under estimates, you can see that sex, the relationship between sex and the intercept for perceived math ability. So basically, remember males were coded 1, females 0. So basically, males started off with higher perceptions, significantly higher perceptions of math ability than females did. In terms of science ability, we essentially had the same thing. This is positive, which is consistent with males perceiving a greater level of science ability at time 1 than females. When we look at the growth trajectories, we see that there is a significant difference. In other words, basically, males exhibited lower levels of change over time in terms of their perceived math ability than females. In terms of science ability, there was no difference between males and females in terms of their rates of change over time. So at any rate, that pretty well concludes this demonstration of latent growth curve modeling using AMOS, where we have two domains of growth that we're looking at.